Okay, let's get started with lecture. We're going to be talking about mirrors, and we're going to do some document camera work. It'll be on the talking PDF, and I'll be actually using a ruler to draw straight lines on my talking PDF notebook. I hope you brought some graph paper. If you haven't brought graph paper, you'll be all right, but you might want to do some practice tonight with graph paper. Before we get started, I have some unfortunate news, and that is people that sit in the back have not been getting their clicker data into the machine here. You may have seen me trying to figure out what was going on with one of the students' clickers, and the student, her device she was sitting in the back, and it just wasn't getting up here. We tried it out up here, it worked fine, and she put new batteries in it yesterday, and all of a sudden yesterday her clicks started coming in. So if you have zip zap for clicking and you know you're clicking, and you've been sitting way in the way back, now you know why I'm trying to clear everybody out of that way back machine back there. You might want to put some new batteries in or something like that. And that's a good procedure to do in any case, because even if you're sitting up front and your battery fails in a test, you're SOL. And SOL is a Latin phrase. It means you're toast. It's Latin for your. That's what, in case you didn't. Kind of like etc. means etc. In Latin. I mean, it's a Latin phrase. Okay, so let's get your clickers ready. We're going to go a ways before we get to the clickers, but we have some clicking ahead. This is diagram 25-7. We kind of skipped over this. Mirrors are important because they are a physical representation of a mathematical symmetry called reflection in a line, or reflection in a plane if you're thinking in 3 dimensions. And symmetries are actually significant scientifically because for every symmetry in nature, there's a conserved quantity. So if you have been wondering, well, Dr. B, why is energy conserved? Why is angular momentum conserved? It's because in the physical system that you're studying, there is a symmetry. And with every symmetry, you can encode a conservation law. And momentum and energy are related to symmetry with respect to spatial displacement and symmetry with respect to temporal displacement, delta T. That's the energy symmetry law. This one, the symmetry here is in front of the mirror and behind the mirror. So this one, the light is actually reflecting off the front of the mirror. So when I say the front, I mean over here where the light rays are, okay? And you're over here, you're up here observing. And the basic fact that you can use to derive everything else is the image of the object in the mirror is as far behind the mirror as the object is in front of the mirror. So this distance here, AC, D0 or DO in the textbook nomenclature, the distance from the mirror to the object, is the same as D subscript I, the distance to the image. And so what that means is, if you may not have noticed it, but you know, if you have a camera, you can notice it. If you have a manual focus camera, you'll notice that if you stand 4 feet in front of a mirror and set the focus manually of your camera to 4 feet, the image in the mirror will be out of focus. Right? You'll be out of focus slightly. If you have a good lens, you can see it. But if you're standing 4 feet in front of the mirror with your camera and you set the focus for 8 feet, in other words, 4 feet to the mirror and then the same distance behind the mirror, then the image in the mirror will come into sharp focus. And that's what this means. And it is significant. And you can actually see it if you're a fair distance. You know, the other way you can see it is if you have to wear spectacles, if you have to wear glasses, you can sometimes see it, you know, with glasses on, with glasses off. Question in the back. It's Anthony, right? Okay. Mark. If some mirrors that you, like the one in your passenger side rear view mirror, side view mirror, that's because they're curved. And we're going to be working on that today. And so you get an image that is closer, the object is closer, it appears further away. Okay? You know, so it appears tinier than it actually is. So it might be like some big gigantic truck, and it's actually close, and it looks tiny in the mirror. That's why a lot of people get, you know, a convex mirror to put on their driver's side mirror, and so they can see, you know, other things besides what's in the standard mirror. I want to talk about the paraxial region, and I've got some sketches that I want to go over with you and just drive home this idea of paraxial and how the whole idea of the formulas that we're going to use today is that they're approximations to the exact positions and measurements of light rays, and they're only good approximations if you're in the paraxial region. So let's take a look at this. Paraxial means near the optic axis. Now I've got a mirror over here in red. That's a big spherical mirror over there, and here's a smaller one up here, and I've marked the center point C. Okay, and that's actually, it's not a sphere, it's an arc of a circle. Here's the full circle. So if if you're thinking about a sphere, okay, you basically just take part of the sphere. This thing over here, this mirror is actually just, so what I did is I took 100 pixel, go ahead and make a sketch of this, because that 100 pixel square is going to be important for us when we get to the big mirror. Okay, and so, when you're doing this on Apple Keynote or PowerPoint, you can't make a perfect circular arc, so what you do is you make a circle and then you block it with a white rectangle. Now, I kept my rectangle red or yellow with a red border, and I typed in the words 100px for 100 pixels. That's the size of it. On my computer screen up there, it looks a little bit bigger, but so that's how I made it. This one over here. Okay? Let me move these out of the way. Now here's the optical axis. Go ahead and sketch that in. And make sure that you have a good amount of curvature for that spherical mirror up there. All right? Now I'm going to trace in below the railing, please. Below the railing, please. Sit below the railing, please. Thank you. Anywhere you want. I'm going to draw on a line, a ray incoming to the red mirror parallel to the axis. Here it is. I kind of burn it in there. Okay, it's blue. It's got a little arrow in kind of the middle of it to indicate the direction. Okay, now that's going to bounce off the mirror. Angle of incidence equals angle of reflection. that will always be true. The paraxial approximation is not going to work with this very well because this is so far away from the optic axis in relation, Megan, to the radius of curvature of the circle. That's about, above the axis. It's a little bit further than the radius of that little red circle. Okay, so that one's, and here's another way to think about it. It sweeps out, let me get this here. There we go. The spherical mirror, it up above the optic, this is about 65 degrees. So the entire mirror, the way that I've constructed it, with a 100 pixel rectangle and a regular circle, and the part that I haven't blocked out is 130 degrees worth of that circle. Okay? And the paraxial approximation means that you want to stay within, a few degrees of the optic axis. 65 is way too much. It's not bad if you're using a computer and constructing the rays, ray by ray, and using angle of incidence equals angle of reflection. That will always work. It will always be true. But for the shorthand formulas that we're going to use, 65 degrees is way too much sweep for a spherical mirror of any size. Now this mirror here is actually 100 pixels. It's actually 50 pixels radius, 100 pixels diameter. All right. Now this big one I've put in the center here. Okay. For this big one, and let's put in the 100. All right. So there's the same 100 pixel rectangle. Now that's just to remind you of how I made the little one up above. Now if we go ahead and say, all right, I'm only going to consider this arc of the big sphere that's cut off by this rectangle, and ignore stuff above the rectangle, and ignore stuff below the rectangle, and just have a little slip of a spherical. That's a very small number of degrees there. I should have figured out how many degrees that is. And you can tell, from the center up to this corner, the upper right corner of the yellow rectangles, it's not many degrees, maybe 10 degrees or something like that. Okay, and similar down to the lower right corner. All right. So you may think to yourself, well, big deal, Dr. B. How does that show that it's paraxial? Well, let's do a little close-up. Now I want you to look at this. This is not the close-up. Here comes the close-up. It'll take a second to render. Here it comes. Come on, baby. Oh my goodness. Oh my goodness. My goodness gracious. Let's see if it's rendered on my screen. It hasn't rendered on the Crestron. What is this? Is that a spot on the screen? All right, I want you to look at it. I'll just hold up my screen here. Let's see if I can do this. Oh, great. Carefully. There it is. And what you're supposed to be seeing on the screen, the cord won't reach. I'll do a PDF of it later. But let's see if this next one will render. There it is. Okay. All right. Now what we're going to do is we're going to cut off everything above the yellow rectangle and everything below that, and we're going to use that as our mirror. It's spherical. And you can see a little bit of daylight between the mirror and the rectangle. All right? Now it's hard to see if you're back in the backed up view, but in close up you can see a little bit of daylight there. That means that the red line is curved. It really is part of a spherical surface. So let's back up. Here we go. And all right, let's just start cutting out that stuff. All right, so we removed that. Let's remove this stuff down below. All right, this is just me putting big white rectangles in to block out the rest of the red circle. And let me get there it is. All right. Now, can you guys tell that that's curved or a straight line? It looks like a straight up and down line, doesn't it? But it really is constructed as a curve. So, excuse me, that really is a spherical mirror. Now, let's put in the optic axis. Here we go. Come on, baby. There we go. There's the optic axis, so go ahead and sketch that in. And the center is here. Get my cursor. Here's center, C2. This is center of the second spherical mirror. Center of curvature for the second spherical mirror. All right. And so halfway is the focus. 1/2 times the radius. All right. And now let me bring in a ray parallel to the optic axis, and this is the one that we're going to use. And now this one is 100 pixels above the optic axis, but you can see here that this is the furthest one out that can be reflected by the mirror. Everything above this goes zipping past the mirror. Everything below it gets reflected all the way down to the lower edge down here. Okay, so this is a representative of some of the parallel incoming rays. And here are the specs. The radius of this circle is 1200. The entire width of my display is 1280, so you can't even see the backside. The rest of the circle is way over here somewhere. Okay, and way up above and way down here. So the radius is 1200 pixels. The diameter is 2400 pixels. The focal point is 600 pixels in from the surface. All right. Now we're going to be doing some calculations on document camera in centimeters, but this one's in pixels. All right. So the upshot for you is simply this: the reason I'm trotting you through these sketches is so that you can believe this sketching, diagramming principle. Everything we're doing is approximations, unless you're programming a computer to do it exactly. So in our sketching, we're going to use a straight vertical line segment to represent the paraxial portion of the spherical mirror, because you could hardly tell it apart from a straight line to look at it. And I made sure that it was all accurately represented and stuff. And then we're going to use 3 principal rays that are mentioned in the textbook. Question over here. Kimberly. So what I'm saying is that you can use any amount of a spherical mirror that you want, but most practical applications take a very small paraxial slice of it, like what we have here. And that's because the equations that help you locate the focus and the image distance and all that stuff is a good approximation if you've only got like a few degrees of your sphere. You know, the first one we had was like 65 degrees, I think. I mean, I measured it with that little line that I had there, okay? And you can do that. People have mirrors like that, but it's trickier to do the calculations for that. But once you're down in the paraxial region, all the calculations are really simple, and we're going to do a few in a minute, okay? And so that's why we do that. So we want to take, you know, no matter what the size of the sphere is, we want to just take a few degrees of it, okay, a few degree circle, and then use that as our surface, and then our calculations are cinchy. Now, somebody like NASA, you know, that has half the computer power in the planet at their disposal, you know, they could do it all. You know, no, they don't have to stick with paraxial. Although, you know, it's still, the thing about it is a paraxial mirror, or a mirror that's restricted to paraxial region, is going to be lighter, and it's going to be easier to build with because it's not going to crumble. You know, it's nearly flat. So making it stable and everything is going to be relatively easy versus something that's got a good 65 degrees of curvature to it. It's going to, you know, it's going to be a little unstable, a little bit less shock-proof, stuff like that. And so Jade, thank you. Monica, thanks for helping hold up her arm so that she can ask a question. Yes, Jade, your question. Yeah, and the focal point is going to change for if you're using more of the mirror, but 1/2 R is pretty good if you're just using the paraxial region. So for instance, if you're making a telescope, you know, the telescope is basically a tube with a mirror in it, and then it you know, reflects and it gets the starlight to focus at a certain point, and that's where you put your photograph and you map out a galaxy or something like that. Or your photo cells, and so figuring out where to put it is one of the things you got to do. And so you can do it with more dish to the mirror, but it's usually for various reasons it's easier to do a good job with really great precision if you have you know, a paraxial, a few degrees of the sphere, or the hyperbola or the parabola, you know, depending on what you're using. Yeah, you want to, if you have a camera, it's just like with your eye. You know, the lens in your eye is designed to focus incoming light rays on your retina. Okay, so if the incoming, now that's a lens, and we're going to study that today a little bit, but if the incoming light rays don't focus properly initially, then you have either nearsighted eyes or farsighted eyes if they don't focus right on the retina. Okay, so that's why you want to, so now if you're trying to build it, you know, God made our eyeballs, but we make telescopes and detectors and stuff, so we got to figure out where to put our, you know, our film, where to put our detectors and stuff, and that's going to be at the focal point. Okay, and so we got to know where it is. And, you know, and so we have to know the curvature. You know, when we make the mirror, we have to know the radius of curvature, and then we got to know where to put the detectors or the you know, the film, and then, you know, but all that that's programmed into your DNA for your eye and stuff like that. But for the rest of us, we have to, you know, actually use equations to figure out where. Yeah, if you don't put your detector or your film at the focal point, it's just gonna be like being nearsighted or farsighted. Matter of fact, the Hubble Space Telescope, when they first put it up, they made a mistake with the curvature of it, and they didn't realize until it was up there that it was nearsighted. that the incoming light rays were not focusing on the detector perfectly. And they fixed it eventually, and it does a great job, but yeah, question?
So when we use a paraxial portion, we use it for accuracy.
Yeah, it's for easy accuracy. Okay. And now, the three principal rays, here they are. Go ahead and make a sketch. Here, this is from the textbook. You take, they use that red arrow as your object. That's typically what we do in optics. And so the tail of the arrow's on the optic axis, and the tip of the arrow's up above it. And it's somewhere, this one is somewhere between the center and the focus, right? But you can put it anywhere you want. And then you got to figure out where to put your camera. Okay, so you can take a photo of it. All right, so one of the ways that you do that is by tracing out rays. The first one is the one that is incoming parallel to the axis. Okay, so that's parallel to your telescope tube, all right, right down the pipe. And then that one is going, if you're in the paraxial region, that's going to go right through the focus. Angle of incidence equals angle of reflection at every interaction of the light ray with the mirror. And if it's a paraxial region ray of light, it's going to go pretty doggone close to the focus. All right, so this is our shorthand ray number 1, and we're going to do some tracing with this on the document cam in a minute. And then after that, you're going to do some calculations. All right, the second one, and this is also in the book, if it comes in, light rays, you can see that little red arrow from any direction. So if that means the light rays are going off in all directions, a light ray that goes off in this particular direction through the focus and then hits the mirror, it will be reflected, angle of incidence equal angle of reflection, directly back parallel to the optical axis. All right? So it's kind of a reverse psychology relative to the first principal ray. All right? So the first one came in parallel, went through the focus. This one comes in through the focus and then bashes back out straight along the axis. Then the other one that they use, number 3, is if it appears to come from the center of the sphere. No. But you can go and look on YouTube later. You want to get the sketch, right? Yeah. It's in the book. Okay. Anyway, so this is the third one that they mentioned. Now, I'm not going to use this one. I'm going to use a fourth one, and I'll sketch this one out. But, you think about it. If it comes right through, if it comes from the arrow, as if it were aimed from the center, that means it's traveling along a radius. Every radius is perpendicular to the surface, or to the arc of the circle in this case, and therefore it comes straight back. Angle of incidence is 0, angle of refraction is 0. It just bounces straight back. Okay, so it just backs up. Right, it goes in as if it's coming from the center, and then it actually does go back through the center. All right. Now, the one that I prefer is a little bit simpler than that. Here it is, number 4. Dr. B, number 4. It's not in the book. Right, so I'll go nice and slow on this diagram. Okay, so go ahead and draw your spherical arc and the optic axis, and park your red arrow somewhere, and bounce a ray of light from the tip of the red arrow directly to the center of the mirror. So that's where the optic axis intersects the mirror. Okay, that's your symmetry point of the mirror. Okay, you've got the same number of degrees of arc above that as you have below it. Okay, now this one's not in the book, but it's particularly easy because the angle of incidence is equal to the angle of reflection, so it just bounces back out symmetrically, just like that. They all bounce out symmetrically, but the ones that are up away from this point are a little bit trickier to graph out. But we have the 3 shorthand rules that we just went, and those are mentioned in the textbook. Okay, and this one's not mentioned in the textbook, but we're going to use it today. Because this one's a little bit easier to draw on a sketch. And that's going to make it easier to figure out just what the heck is going on. Kimberly, do you have a question again? Go ahead. It's all right. Go ahead if you want. Yeah, this one doesn't go through the focus. It goes from the arrowhead to the symmetry point on the mirror. You know, where the optic is. So this one goes, the optic axis goes straight down the pipe. The mirror is centered. Okay? And so if you hit at that symmetry point of the mirror, that's the very center of the mirror. I mean, if you have a circular tube and a good spherical surface, that's the very center of your mirror. And it bounces back out at an equal angle. And it's easy to graph because it's right by the optic axis. And we'll graph it here in a few minutes. All right. Now, has everybody got this diagram? You got it? You got it? Okay. Ready to go? Okay. All right. Yeah, this is a famous drawing by M.C. Escher. You ever see this one? It's M.C. Escher looking at himself in a spherical convex mirror. All right? And here's a close-up. You can see his library back there. That guy, M.C. Escher, was amazing. Now, for a convex mirror, it's a little different. And we're going to do an example of this in just a minute. But we're going to use the same rays, but for a convex mirror, the focal point is behind the mirror. So when I say behind the mirror, that's on the other side. You know, all the light sources are out here. Here's your observer. Okay, your object is out here. But the image appears to be back here behind the mirror. And it appears to be smaller. You know, just like this picture of M.C. Escher. You know, you can see his hand. You know, so his hand is approximately the size. I mean, if you'd have spread his hand out, it would be about the size of that sphere, right? But in the sphere itself, you can see most of M.C. Escher. He's sitting down in a chair, I guess. Okay, so that image of M.C. Escher, and you can actually see his hand down at the bottom. But that image of M.C. Escher is smaller than the object. You know, the real M.C. Escher is, 6 foot tall or whatever he was. Okay, but he's definitely not 6 foot tall in that image. And it's an upright image. It's not upside down. You know, if you look at stuff in a magnifying glass, sometimes if you don't look at it right, it's upside down. So. But anyways, so we're going to do an example with a convex spherical mirror. And they're the 3 rays, number 1, incoming parallel. Number 2, coming in through this far focal point. So it's a slightly different tilt because the focal point is over here. All right? And so this one goes in towards the focal point and then bashes back out straight along. And this one, number 1, comes in parallel to the optic axis, and then it reflects as if it came from this far focus. And then number 3 is going straight to the center of curvature. All right, so let's go to the document camera. Let me pause the YouTube for a second. Now, your diagram, just to reinforce, your diagram, if you're doing it on notebook paper or something, it might not look as sweet. Mine was pretty good. And I've actually done it twice today. I made sure I did it once and everything worked out good. So that's the second time I've done it. So you go home and get some graph paper. Don't make the graph paper blocks too small. See what you can do. You know, do a little practice with it. See if you can make a decent image. Now, I can't test you on that. You know, Scantron doesn't admit sketching. But, you know what? The final exam, I could maybe do something like that. Because I could give everybody a piece of graph paper in their final. And then I could just, and it would be easy to graph. I mean, it'd be easy to grade. You know, are you at 6.9 or not? And I'll think about it. And I'll let you know if I decide to put something like that on the final. Okay, so we're rolling with the YouTube again. All right, here you go. What's the image distance? DI, different lens or different mirror. Radius is 24 centimeters. So put it together, take a few minutes and just go, you know, Lexus, just, you know, talk with your neighbors and everybody talk with your neighbors and kind of work it out and check your sketch. If you have graph paper, you can actually make the sketch. Now this one's concave. So this one, it's all going to be in front of the mirror. So you don't have to worry about the negatives that we just did. This is like the first one we did. Oh, sorry. Okay, you should be able to get Go Nitro and stuff now. Bernard and Cherazar, are you here? You're Bernard. Can you come see me after class? No, it just depends on, you just got to work it out. There's, and that's for a single lens, and then if you use more than one lens, and then it's, you know, and you know, if you have a camera, probably the iPhone camera or whatever your telephone is, the lens in it is probably a compound lens. In other words, a diverging lens, you know, like the convex mirror is diverging, and the concave is converging. And lenses are like that too. And so a complex lens, to correct for aberration and stuff, they'll put more than one together. And sometimes they'll put two of them like this, and then they'll bring them, like this. When you focus, you're bringing them closer and further apart. So there's a lot. I mean, this is like optics 101. Yeah, and then you got to do it again, so that where it lands on the other mirror, then you got to do the same, And if it doesn't come in parallel, or to the focus, or to the symmetry point, then you got to do a lot of calculus. Question? Would there be a situation where what? Yeah. Well, like in a makeup mirror, if you hold the makeup mirror just the right distance, your face just gets bigger and bigger, and then it disappears, and then it flips over. Did you ever notice that? Do you have a Yeah, so if you have a spherical mirror and it's a diverging, a convex, then if you put it at exactly the right point, no image will form. And all right, 30 seconds. $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, most of you guys got it, 48. And just to double check, here's the calculation. Focal length is 1/12. It's positive because this is a concave mirror. So, and then object distance is 1/16 or 16. So your fraction is there, and common denominator is 48, et cetera, et cetera. And this is another example that if you get some graph paper and start graphing it up, and use the methods, don't make your object too large. That's the key. I used 2 blocks for my image, and my mirror was about 2 blocks high, 2 blocks down. That should be enough, unless you're way far away or really in close. But this one you should be able to graph up. Before we continue with chapter 26, I just want to make a point that I really like problem 38. And problem 38 is actually in the Student Solutions Manual. Now, why am I making a note of that? Because I think that the written homework, number 5, is going to go out tonight. And I particularly find problem 38 inspiring. And therefore, if you want to think about what I'm thinking about, you'll think about problem 38. And you may just find that it's a happy day when you get to the written homework. Now, I haven't written the written homework assignment yet. I'm still thinking about it. All right, chapter 26. Question? You can't really say it's always between the center and the mirror. sometimes you just have to work it out because it depends on the focal length, the size of the mirror, and where your object position is. So if your object position is between the mirror and the focal point, or between the focal point and the center, or past the center, or past the other 2 times the center, 2 radii away, or more than that, you know, and if it's convex, also you got to think about that. So you just got to work it out. But and the numbers will do the talking, and you may not be able to draw it very easily, but then the numbers will do the talking, and you just go with what the numbers say.
When we're saying that the image forms like behind the mirror, in the convex, it's like behind like the surface of.
Yeah, so the front of the mirror is where the light rays bounce, you know, they reflect. Angle of incidence equals the angle of reflection. And remember how on that second example I did the dotted lines behind the mirror? And then those weren't real light rays back there, but they were kind of virtual light rays in that that's where the light rays appeared to have come from. So that tells you where the image is. So like when MC Escher is looking at that thing, at that sphere, he's not taking those 2 rays that we had. He's taken probably a bunch of parallels that come out in his direction. Okay, you know, we only did 2, and we're just trying to figure out the tip of the arrow, but he's looking at the entire thing. So it's pretty complex. There's a zillion light rays in that image, but your brain processes them all, and you know, you make sense of it. All right, chapter 26, refraction. First thing I want to go over with you is Snell's law. And here's a diagram. Refraction is something that occurs at the boundary between 2 different material media through which light is propagating. And it can be visible light or ultraviolet, X-rays, anything can refract. I mean, theoretically. So there has to be 2 different media, and the 2 different media have to have different speeds of light. So this example in this diagram from chapter 26 is light rays going from air, which is almost exactly the speed of light in a vacuum. You know, so 299.779 or whatever it is. And then it goes into water. And when that happens, the light ray changes its trajectory. Now, I'll get to a physical explanation of that in a second. If the light rays are reversible, so if you go to the same angle down in the water and you shine your flashlight up out of the water, that's diagram B here, then it'll follow the same. So the refracted ray is this one that's, let me get this over here. This one here that's going upward out of the water. So refracted light rays, will, you know, you figure out the trajectory it holds for stuff going out as well as stuff going in at those angles. Now, if you have a different angle, you got to recalculate. And this is the formula that you use. This is Snell's law. N1 times the sine of angle of incidence number 1. Okay, so that's this angle right up here, is equal to N2, the index of refraction, for the second substance times the sine of the angle of refraction. So this angle here, theta 2, is not an angle of reflection, and it's not an angle of incidence, it's an angle of refraction. But it's measured relative to the normal, so between the normal and the ray. And down here, theta 2 is in the water. It's from the ray to the normal. Okay, so here's the normal, this black dotted line. You may be saying to yourself, Dr. B, what the heck is an index of refraction? Well, the index of refraction is basically the ratio between the speed of light and the speed of light in that medium. So the speed of light in a vacuum is the symbol C, and then the speed of light in that medium. You know, so you don't go quite as fast through glass. You know, photons don't go quite as fast through glass as they go through air. And they don't go quite as fast through air as they go through a true vacuum. Okay, air is pretty close to a vacuum as far as light rays are concerned. You know, and the index of, there's a table of indices of refraction in the textbook, and if you look up the index of refraction for air, it's like 1.000293. In fact, we're going to calculate with it in just a second. All right. Now, there's all kinds of phenomena and devices and stuff that display or make use of refraction. You know, for instance, lenses. If you wear glasses or contacts, they make use of refraction from the air into the glass or the plastic that, you know, your lenses are made from. You know, everybody has a lens in their eye, and I don't know what that's made of. Collagen or I'll have to look that up. I'm not up on anatomy, but you know, light goes through there pretty well. And then the inside of your eye is made of water, pretty much. Then rainbows. There's another phenomena that you know, is we see that the dispersion of light from raindrops. What happens there is sunlight goes into the raindrop, refracts, and go ahead and make a note. Every wavelength of light diffracts slightly differently. Every frequency or every wavelength. So 436 nanometers will refract has an index of refraction slightly different than lambda equals 656.3, the H alpha line. You know, in glass, and that's for glass, plastic, air, what have you. All right, and so in a raindrop, the water, the red diffracts a little bit differently from the orange, the yellow, the green, the blue, indigo, and the violet, and then it reflects off the back of the raindrop, comes back to the way it came, and then when it leaves the raindrop heading for your eyeball, it refracts again. So the colors are even more spread out after the second refraction. And sometimes you get a double rainbow, that's from big raindrops, in which you get another two more reflections in the raindrop, and if the angle is just right and the size of the raindrop is just right, I get another reflection. You know, so some of it goes out, the first rainbow, and from that point, some reflects, just like in this image. You know, this is a reflect every time you have, most of the time, every time you have an interaction between a light ray and this boundary, you're going to get a little bit of reflected light and a little bit of refracted. All right, so if it's refracted on the way out, and then some of it's reflected back into the droplet, and back to, and then it disperses. Okay, and then it reflects off the back, and it disperses again on the way out, and that's how you get a double rainbow. There's a nice diagram of it in your textbook. All right. Now, the physical meaning for light bending is, go ahead and make a note, figure 26.7. And this is a really nice diagram because I always like to compare it to a marching band. And you know, if you're in a marching band and you're going straight forward, you know, everybody has to go the same speed. And then if you start next to your neighbor and you're going the same speed and you're going the same direction, you stay right next to your neighbor. But if you start going slower than your neighbor on the right, he's going to get ahead of you. And if he starts going slower than the neighbor on his right, then that second neighbor out is going to go a little bit faster, and he's going to get in front of you and in front of your neighbor. And so when you change the speed, you can get a maneuver, you know. And raise your hand if you've ever been in marching band. A bunch. And I saw you nodding your head, right? And when you know, I've never been in marching band, but when you're trying to do a turn to the left or a turn to the right, somebody's got to really take long steps, right? All right? And somebody's got to take little tiny steps on the inside. Or nothing. I mean, not even move. Yeah, so that's what this is like. So this is like this weird, you know, this weird quadrilateral up here. That's it. All right? And they've got lambda 2 and lambda 1 marked in over here. And go ahead and make a note. The thing that's constant at the boundary is the frequency of the light. The wavefronts hit and leave the boundary at the same frequency. At the boundary, the frequency of the light incoming and the frequency of the light going through the boundary is the same. So F1 and F2 are the same, but because the speed of light is different, lambda 1 and lambda 2 will be the difference. And so that's like taking bigger footsteps and shorter footsteps. And so the result is you take a little turn. So that's what refraction is. Physically, and the reason that the frequency is the same is that conservation of energy has to hold. Conservation of energy has to hold at the boundary. The frequency is the same. What changes is the wavelength. So some people are taking shorter steps, other people are taking longer steps, and the people taking shorter steps are on the inside of the curve, and that's what you got here. And that's all controlled by the speed of light in that particular thing. All right. I want you. I'm gonna give you a study assignment tomorrow. Tomorrow's Wednesday. All right. And I want you to read in chapter 7, 26. I was going to do this on document, but we need a little bit of time. In chapter 26, read about total internal reflection of fiber optics. And it's basically an application of Snell's law. And there's an example in there. It's a multi-step or multi-concept example. Right now, we're going to work through an example of that, but with real numbers tomorrow on our document camp. So that'll be the first thing we do. And then, you guys have been asking me well, Dr. B, what sections are going to be on the test? Here's what I want you, here are the sections I want you to prepare for tomorrow. 27.1, 27.2. And if you can get through, skip over to 27.5 and read about diffraction and look at diffraction videos on YouTube, you'll be helping yourself out. All right, that's diffraction is going to be the last topic that we cover in chapter 27. So, all right, you're dismissed. I'll see you tomorrow. Come up here if you want your homework.